Hi, this is my second devlog video, and this one is going to be going over the analog circuit display mesh. Not the actual circuit solver, just the mesh that displays voltage heights and currents. To fully explain this, I need to go over how shaders work and how to create custom meshes in Unity. So let's start with shaders. So to do that, I have this scene set up in Blender. So for each pixel we want to render, this ray is going to be shot from the fulcrum point of the camera through the pixel we want to render, which here has been mapped to the camera plane. So you can see it's hitting this green pixel, and then it goes out into the world until it hits an object, or until it hits a bounding box. Bounding boxes will be very important later, but the main thing you need to know is that if the bounding box is within the camera's field of view, it will check if it needs to render that object. So as I move this monkey head off screen, you can see right here it's actually off screen, but it's still rendered. If I move it until its bounding box is off screen though, it will disappear entirely. This is called fulcrum culling, and if you look at occlusion culling in Unity, it will also show you fulcrum culling. So anyway, that ray will hit this object's bounding box, which since it's a cube will probably just be exactly the same as the display mesh. And then it will take the vertex positions closest to the point it hit and interpolate those to find out what color this pixel should be. So here it's pretty simple. We can look at the UVs down here, and we can see between those two pixels it's green. But this is kind of wasteful. But realistically we would have something closer to this, just 8 vertices for the entire mesh. So when it hits this point, it's going to look and see these 4 vertices. And if we look at the UVs, you can see first off that it's floating in space. But since this texture is tiled, we can just shift it down by a whole number of units and actually see what the renderer is going to see. So now you can see these 4 vertices both in the UVs and in the viewer. So if we make a new vertex right where the raycast hits the object, we can see where that would be on the UVs. This is basically what interpolation is doing, is just seeing which exact pixel the ray is hitting, and then returning that color to the shader. Okay, so now let's look at an actual Unity shader in Visual Studio. This is a shadeless texture shader I made, which doesn't take in any lighting into account. All it does is return a texture. So this is about as simple as a vertex fragment shader as you can get. For properties, we just read in a color texture. If you look in Unity at this shader, you can see it asks for a texture. It also asks for a render queue as geometry, which is later down here in the tags. Its default queue is geometry. Next, we declare the vertex and fragment functions, and then we declare the color texture that we asked for earlier. Next, we have vertex input, which is just the data we want the shader to read out of the mesh. So we want the vertex position, which you have to get, otherwise the shader just will not work, and the texture coordinates, which is the UV map. Then we have texture output, which is pretty much the same thing, just what we want it to remap to. Then we have the actual vertex function, where we take those inputs and map them to outputs. The part where we get to have fun is the fragment shader, and as you can see, no fun to be had here. We just read the texture using the UV coordinates and return it. So that's it. So here is that shader in action. It takes the texture and outputs it. That's it. So that's basically how a shader works. I'll go over how this shader works in a while, but first I need to go over how the mesh it's on is generated. So this square right here, I'm actually generating through code, and if I click into the game window and press R or F, I will move the UVs, which will scroll through the part of the texture you can see. So here's the code for this. We start off by getting the mesh filter, which is just this component on the object, and if we exit the game, you can see the default is no mesh at all. If that was not the case, or if we were generating a second mesh after the first one, or completely overwriting it, we would need to run mesh.clear in order to clear out the old data. Before that, we grab the mesh from the mesh filter, and this is a reference, not a copy of the object, so we don't actually have to copy the mesh back to the mesh filter. It's just a reference, so every time we change anything on mesh, it's automatically updated in Unity. The first step of actually setting up the mesh, though, is assigning the vertex positions. And to do this, I actually have drawn out the mesh I want to make in Blender and labeled all the vertices. So you can see vertex 0 here is at 0, 0, 0, vertex 1 is at 1, 0, 0, 2 is at 1, 0, 1, and this is all mirrored in the code right here where I've copied it in. Now, by default, Blender and Unity don't have the same coordinate schemes because in Unity, Y is vertical and in Blender, Z is vertical. So you have to apply this 90-0-90 rotation to the object to actually get the coordinate schemes to line up. But after you've done that, you can basically just manually copy all the data points from Blender to Unity. Next, we declare triangles, which is just saying connect vertex 0 to vertex 1 to vertex 2. So the important thing about this is that they go clockwise from the normal side. So you can see this is the back of the mesh, this is the front. So we need to go clockwise here, and it doesn't matter if we start on 1, 2, or 0, as long as they go in that order, 1, 2, 0, it will draw correctly. Next we have UVs, and honestly you don't need UVs if your shader doesn't use them. You can create a mesh with just these 3 lines of code. But since we do need UVs, we're going to once again copy them from Blender. So you can see here, I have vertex 0 is at 0, 0, vertex 1 is at 0, 1/8, and so on. But this doesn't look right, and the reason is because we have interpolation turned on. So if we switch interpolation to closest pixel, it once again looks correct. And you can see if we move the UVs, it gets mirrored in the actual mesh. The same thing needs to be applied in Unity, so we'll take this texture and apply point filtering, which is to say no filtering on it. That way it just returns the raw pixel values, because this is actually an 8x8 texture. So now we just copy the UVs from Blender. Next we have recalculate normals and recalculate tangents, neither of which I need because this shader just uses UV coordinates and no other data. And finally we have recalculate bounds, which calculates that bounding box I showed earlier. You generally don't want to run that every frame just for efficiency reasons, but you do need to run it if you move vertices a significant distance. So let me show you what happens if we don't. So I've set all the vertices to be at 10, 10, 10, and then in update they are set back where they were before in the square. So if I run this, you can see there's nothing there, but if I move it until this square, which I've put at 10, 10, 10, is in view, if the center of it is in view, that square appears, and if it goes out of view, it disappears, because as far as the renderer is concerned, this square is up at 10, 10, 10 because we never updated it when we moved the vertices. And let me comment that back out, and finally we have the inputs which move UVs. Generally you wouldn't read straight from UV textures, because generally I keep everything stored in its own UV array because I'm updating things in the UV array a lot more than I'm actually updating the mesh. But here I just directly updated it. And my point with this last bit is that it's really this easy to change mesh data. You just directly edit it and it just updates. So finally, let's move on to the actual analog circuit mesh. Starting with the shader, I don't want to go through line by line, so instead I'm going to frame this around the textures. So the main one you've seen already is this color texture. So all of the tiles get scaled down until they fit within 1 pixel of this 8x8 texture, so that the entire tile is one solid color. A very simple texture is this reflection map, which just gets used as a reflection map, nothing fancy about it at all. And this is just a placeholder texture, so it really doesn't matter. The complicated ones are the main texture and the electron texture. These textures are either created or edited through Blender. So what I have open right now is the main texture's red channel, which is stored in its own collection and also in its own render layer. So if I look down here at the render nodes, you can see it's right here as the main.r icons. So then that gets turned into a monochrome texture, which is what this does, which gets fed into the red channel of the main texture. In the green channel is this reflection map, which actually looks like this, all grainy. I'm not sure why that happens, but running it through a color ramp removes all that graininess. The blue channel is just this accent color, which you can see adds in here. It just looks a little bit bland without that, but it really doesn't do much. So this is where it gets a little bit complicated. The alpha channel is a mask. Parts that are black get this full reflection texture. Parts that are white get the reflection texture unless there's a wire there. Dark gray parts have no reflection texture, and this middle gray color gets no reflection texture, and a wire can be there. All of this gets processed through the shader by multiplying and shifting the value around so that that one specific shade of gray multiplies something by either 1 or 0 to add or remove a wire or the reflection texture. The electron texture is a little bit more straightforward. You can see this first channel is the electron texture that you see scrolling in Unity. The green and blue channels are the red and green channels of a normal map texture. This honestly shouldn't be on the Electron texture, but it had some free channels and the initial main texture did not. The problem is these 5 textures, these 2 and then the normal map counted twice, all need to be projected on UV channel 1, and the Electron textures, this actual texture and this mask, need to be on channel 2. So to explain how all these textures are used, let me show you the prototype mesh data in Blender. Just like last time, I have all the vertices numbered and the UVs set up correctly. And you can see UV channel 1 here is pretty much exactly what you would expect a UV to look like, just a top-down view. And you can see the main texture actually lines up pretty well with it, and you can kind of see how this matches what you see in game. The distracting part is these symbols are clearly too small. They're actually at 1/8 scale. And the way this works is that the UVs looking like this and like this are exactly the same. The texture repeats. So it doesn't matter how many whole numbers the UVs are offset by, it will look exactly the same. The thing is, if I move this up by, say, 2 units, and then scale everything down by 1/8, it now lines up with this symbol for alternating current. So symbols are selected by moving the entire UV by whole numbers, which doesn't affect the normal UV projection, it just affects the symbol. Now for the wires, those are a little bit simpler, but doing pretty much the same thing. If I switch over to UV map 2, you can see these 2 triangles are on the left side and the rest are on the right. And if I load up the Analogue Electron texture, you can see the left side lines up with nothing and the right side has this line going down the middle. That line is the mask for displaying a wire and the wire texture. So to show or hide wires, we just move the UVs left or right 0.5 so they line up or don't line up with that wire mask. And to animate the texture moving, we move the entire mask vertically on the y-axis. So this all finally brings us to the actual mesh generation for the analog circuits. So let's start by looking at load circuit, which starts by loading up the actual file. Then there's some initial stuff like reactivating the wall render mesh, checking if text display and bridges need to be used, but then we actually get into the loading. I'll skip the binary loader for now because it's a little out of date, but then we actually read in the data, set up the number of rows and columns in the analog circuit, clear everything, initialize a bunch of variables. Then we call initialize arrays, which sets up all the arrays we need to store all the data for this mesh. So tile used is just a boolean showing which tiles need to be hidden. Height is showing the voltage data. Type is just a number between 0 and 63 showing which of these tile types each component is. Wire used has 8 values for every tile showing which of the 8 wires is actually going to be active, and that's represented as a value of 0 or 0.5, which is the offset that's applied to the UV channel. That way I can just directly read the float in. Wire current is actually the current in each wire, and that value is used to offset the UV2 channel every frame to show the wire current moving. Tile bridge index stores a reference to the bridge that's used by each tile, which I'm not going to go over. Bridges are an entirely separate mesh, so we don't need to deal with them, and some circuits don't even have them. Colliders is, once again, just a 2-dimensional array of all the colliders that are needed on this. Then wire currents are all initialized to 0, since everything else in the code just offsets them. They need an initial value. Getting back to the load function, we now just read in all the data from the text file. So whether the tile is used, what type it is, and what the constant is, or like resistance or capacitance, is associated with each tile, and all that gets loaded into those arrays we just initialized. We then read in which wires are used, and then we finally move on to actually initializing the mesh. So starting off, we apply the right material to the object. Every time the mesh is unloaded because the player walks far enough away from the circuit, we swap materials to one that's much easier to render and looks better at a distance. So we need to swap back off of that to the one that actually displays data. Now we initialize all the arrays that are going to store the vertex data. You may notice tile count is rows times columns, which disregards tiles that might be hidden. I found it's much more efficient just to initialize arrays that can contain the entire thing, even unloaded tiles, rather than trying to work around tiles that are missing. This way I can just address things by their row and column instead of having to use like a dictionary to look things up or having to store which vertices to skip over. So we set the vertex count to the tile count times 56 since there are 56 vertices in every tile, and then we set the triangle to the tile count times 72 since that's the number it takes to make all the triangles we need. We also initialize the walls at the same time, but I'm not going to go over that because it's pretty much the same process, just a little bit simpler. Skipping bridges, now we have this nested for loop to loop through every single tile. So every tile, we assign a tile location, and then we check if it's actually used. If it's unused, we scroll down here and set all the vertices to be exactly in the center of the tile, and then we don't generate any triangles for it. I believe if we left the default, they would all be at 0, but I'm not sure how it would affect performance to have a couple hundred invisible vertices all at the 0, 0, 0 point. So if the mesh does exist, we start by setting up colliders. Every tile gets a box collider, and we don't currently know the height of any of the tiles because we haven't run any of the simulation yet, so I'm just creating it and throwing it down in the right spot. When we do actually update the heights, it will update for all the tiles that have a voltage, but all the ones that don't will keep this default value, so I set this to be the height of a tile that's currently at 0 voltage. These two variables just store the data we're going to need for the UVs. Next, we set the tile vertex index, which is the index of the first vertex of this tile. So now this for loop just loops through every vertex in the tile, setting its position based on prototype data and the tile's center position. That prototype data is stored down here, and this is just data read straight in from that Blender prototype file. So I grabbed vertex 0, read its location, and just typed it out into this array. I also have prototype data for both UV channels and the triangles. Getting back to this for loop, the vertices are read in from that array I just looked at, as are the UVs. But they're also offset by the type column and type row, which are whole numbers. Just like I said earlier, the entire UV is offset by a whole number. That way, its reading of the normal texture looks perfectly fine, but once it's scaled down by 1/8, it will line up with a different symbol or a different pixel on the color texture. Also, I assign normals here, and since these are in local space, all of the normals are just straight up. I then use array copy to copy the UV2 channel information into the mesh, and the reason I don't apply any offset to this is that every frame the wire updates, it's pulling this data in again. I then loop through all the triangles I'll need, and I add in the vertex index to all these. That way it's offset to read in the vertices from this tile instead of the last one or the first one, which was a bit of a bug I had early on because I just drew all of the triangles from the very first set of vertices over and over. Then the same thing is run with walls. The one interesting thing here is that where I have the type column and type row offsetting, and you just scale everything down to get the color and symbol, in walls can be as tall as I want. And the problem with that is that their UV map can go beyond a single pixel. So you can see here, if a wall gets too tall, so it has too high a voltage, it can clip into the next pixel, which isn't good. So instead, everything is stored on the y-axis. Then when it's read back in, I take a modulus 8 of that coordinate and divide that by 8 to get the right pixel location on the x, and on the y I just divide by 8 twice. Getting back to the mesh setup though, we're pretty much done. We just clear the mesh and then import all of the data. So vertices, normals, both UV channels, triangles, and recalculate tangents, which I'm pretty sure I don't need at this point. I'm not sure if the lighting data needs it, but I'm just going to leave it until I get back to editing the shader. And with that, the mesh is fully set up. We then set up the text and bridges, which I'm not going over, and then we actually run the simulation to update all of the data. So after all this initialization, during actual gameplay, all that's really updated is the voltage and current values, which is to say tile heights and the scroll speed of UV map 2. So that's a 20-minute explanation of how all this works. In a future video, I'll go over how logic circuits work, which are a lot more straightforward in that there's none of this weird texture mapping stuff. but it does get a little weird with how everything's stored, since analog circuits have a fixed number of vertices since the moment they're created, and logic you can constantly add and remove gates and wires. But I will go over that in some future video, probably not the next one. Anyway, I hope you found this interesting. It was certainly a time investment on your part. Anyway, thanks for watching. Bye.